So I'll be talking about Lifshitz solutions in string theory. And so this is not going to be, I guess, any cosmology here, so I'm not really sure why I'm here. But maybe I'll tell you something. So this is going to be based on these two papers I've written in collaboration with Luke Barclays, Ruth Gregory, Gian Massimo Tassinato, and Susha Parameswaran. And in fact, yeah, this is going to be is work done in the context of the gravity gauge theory duality, which has provided lots of interesting insights into strongly coupled field theories. And moreover, more recently, it has also triggered lots of fruitful investigation in condensed matter physics systems, which present strongly coupled phenomena. And so by its nature, the ADS-CFT concerns scale-invariant boundary theories. However, one may be interested, precisely from this point of view, in more general scalings, in particular for the purposes of this talk, in what is called as the Lifshitz scaling. So in cases where I hope you see this scaling, so if I scale the space-time directions by some constant, the time directions are scaled by a power of such constant. So this was proposed originally in 2008 by Cackrell, Liu, and Mulligan, and from a bottom-up approach. That is to say, they just built up some action which consisted of some coupled by Chern-Simons term, one-form and two-form gauge fields. And in fact, this non-trivial anisotropic Lifshitz deformation of ADS space is sourced by such non-trivial matter. And you can see this from the equations of motion, Einstein equations of motion. And there you have your geometry, in fact, which has this anisotropic scaling of time and space. So we see here that for z equals 1, we go back to ADS. And in pictures, if you want to imagine how is this, so as you go towards the boundary, it's like the time direction is being squeezed much faster than space. Now, it has been argued that this scaling is problematic as r goes to 0, and not surprisingly, right? Because you have this different scaling. However, in spite of this, bottom-up models have been very useful to explore precisely the possibilities of Lifshitz scalings. And moreover, they have been very useful to construct analytical black holes. And in fact, several analytical black hole solutions have been constructed by just adding the necessary fields you need to find such solutions. However, we would like to actually have some more confidence into the holographic dual field theories. And in fact, we would like to embed these solutions into string theory rather than just having some empirical models. So this is what we did by using a trick. So what we did was just to take 6-dimensional and also 5-dimensional, but in what follows I will always be talking about 6-dimensional Roman supergravity, which can be obtained from a consistent, from type 2A massive supergravity in 10 dimensions. And then doing this, then when you uplift, you obtain precisely Lifshitz solutions in 10 dimensions. And so the 6-dimensional Romance gauge supergravity, in fact, can be obtained from type 2A massive supergravity on an S4. And it contains a dilaton, a 1-4 field, a massive 2-form, a non-abelian gauge field. So this is the matter content, and we have indeed, we see these Chern-Simons sort of couplings. Of course, once you have more dimensions, you would like to preserve such structure. And here are just the different fields. So the solution, so we can just solve the questions of motion. At the end of the day, what we find is, in fact, Lifshitz solutions in 4 dimensions, which has a compact hyperbolic space carrying some flux. And then in order to preserve this different scaling for space and time, we turn on this F3 flag, so the 3 component of the non-abelian field, like this, as well as this 2-form field. Okay, so this is in pictures how the solution looks like. And once we have this, we can, oh no, let me give you the, so okay, these are the charges for the different fields. And in numbers, what we have is these parameters, which have a hat because they have been rescaled by the length scale I have introduced here, as well as by phi 0, such that they look quite nice. And so what we have is that for given supergravity parameters G and M, we can tune our L and dilaton in such a way that we find a solution, Lifshitz solution, for any value of Z. Now, if you look at this, these are positive numbers, so we have 2 branches of solutions, but not for all values of Z, because there's a minus sign here. I just mentioned that there's also a family of ADS solutions, because we use very much this knowledge in order to learn more about more general solutions and to trust, in fact, what we were doing. And I'm not going to really explain this, it's just what happened when we did this. So we look at the general radial equations of motion as from a dynamical system point of view. The fixed points are pure exact solutions, ADS or Lifshitz. And then if you do a critical point analysis by perturbing around such solutions, you can explore the different, characterize all the different asymptotic behaviors, even by the eigenvalues of such perturbation. So on the ADS side, when you do that, you can identify very clearly what the black hole, where the black hole is. But let me just go directly to the black hole solution. So we learned from this analysis that in the Lifshitz size, when we look for black holes, I mean, it's not obvious because I didn't explain, but more or less you can see what we found is that all the fields have to be active. And so what we did was just take a suitable answer that looks like a black hole. So you expect GTT to change with R, in particular to have a single 0. Instead, the GRR component to have a single pole. So you put suitable boundary conditions. We took this area gauge here, which we are saying the space is just being scaled by R squared. And then you also may expect this, the size of the hyperbola to change.
So these are k equals 0 black holes?
These are, yeah, flat. Mm-hmm. And so we are using as a asymptotic solution the Lifshitz we found, and the Lifshitz we found are flat.
Yes.
So yeah, so then we have also to put some functions of R in the 2-form fields and in this non-abelian field. And of course, the dilaton also has to depend on time. So you put your suitable boundary conditions, and then again we learn from the previous analysis that the solutions are characterized by the solutions we look for are characterized by the scalar charge and gauge charge. Initial data at the horizon. We fixed the horizon size to 1, and then, well, you just have to look for your solutions, integrating out from the horizon, and looking, of course, for regular solutions. So then, yeah. So let me explain what we found from the numerical analysis. So of course we had to do this numerically because analytic it was too complicated, and we really tried very hard to find something analytic, but that was not possible. So let me say first for a fixed set, fixed value of set. Here the code of the colors you see here. So F, remember, is the GTT function, so the Newtonian potential. D is the radial, the GRR, and then H is the size of the hyperbola. This is the gauge field and the scalar field. So in the two plots upstairs, we are changing the value of phi at the horizon, phi 0. So what we see is that well, this Newtonian potential has a peak near the horizon, and as we increase the value of the dilaton, it does increases also this behavior. And while the radial metric function is relatively well behaved, but notice these sort of wiggles here. And moreover, we see that if we decrease the value of the scalar charge to also negative values, you do approach a sort of extremal limit. In the next plot, what we did is change instead the value of the gauge charge, and what we see is that so here is going up, and then the ones down are going down, and so all the colors and the shapes of the forms of the lines are telling what's happening. So we see that if we decrease the gauge charge, this increases this effect near the horizon, while if we increase the value of P0, so like charging up your black hole, it does go to a sort of extremal limit. So I think I have summarized that there. Yeah, so essentially if you compare this, well, we compare this with what we got from the ADS black holes, which we also found numerically, you get lots of features near the horizon. So then we have the effects of changing the values of Z. Here's the codes. And so we see that if we increase the value of Z, almost, expectantly, this calms down the potentials, and of course the Lifshitz asymptotic is reached more rapidly, and this of course is expected because there is the dependence on sets on R. And however, notice this strong modulation of, well, some modulation at least near the horizon, which may be suggesting something suspicious about this area gauge that we took. And this may tell us that the numerics is missing some exotic features near the horizon, or suggest some possible instability. So all these effects, more or less, that I have described can be also observed when we look at the temperature and the entropy as well. So we look at the temperature, we took a fixed value of Z in order to see what are the effects of changing the scalar charge. Here what happens is that here we start with 0 scalar charge, and then we vary the gauge charge in this direction. Then what happens is that as you increase the scalar charge, first the temperature seems to increase, but then as you increase further, then the temperature decreases. And then for the gauge charge, we also saw this in the previous plots. And so instead here we change the value of the scalar charge, and then for different values of the gauge charge. So we see that the range of possible values of scalar charge is reduced until eventually there's no black hole. And so the set dependence, well, here we took just phi 0 equals to 1. And yeah, so okay, so here we see the effect of increasing the value of Z more dramatic, and it seems that the change in Z, as we see, scales away T away from 1. So of course the numerics are not so accurate to say this is so, and also we fixed the value of R plus equals to 1. And then we did this also for different initial values at the horizon of the scalar and gauge charge. And we see that things seem to fall apart as you increase Z, even if the geometries look smoother for higher sets. So let me skip the entropy, because essentially you can more or less follow what we saw before and see something interesting when the scalar charge changes. So let me just summarize. by saying that we have developed a prescription to embed the Lifshitz solutions into string theory. Well, what I mean here is into some supergravity which can come from string theory, and in principle for any value of set, but there may be issues if you actually take into account more carefully the compactification on the H2. And we found that the structure of the black holes is very rich, but of course most of the work had to be done numerically. And well, we saw the Lifshitz black holes seem to be rather involved. All fields have to be switched on. And we have strongly distorted geometries near the horizon, but this may indicate we just need to change a different gauge. So how about analytic solutions in proper supergravities? Well, we found solutions for systems like this one. However, they don't match any actual supergravity that we know. That's it.
Are these really this black hole? Because there is no Lorentz invariance in this system, I wonder if there is any causal structure corresponding to black hole.
Yeah, there is a horizon, so you have...
I mean, what is the speed of light in this solution?
Well, related to what you have from your GTT, right? So to have a black hole, you just need to have a zero in the Newtonian potential.
The problem is the causal structure of this solution.
I don't think there will be a problem with the causal structure. So you have a horizon. Or different, yeah.
One more question?
Yeah.
I'm sorry.
I don't know.
Go ahead.
Well, I'll do it first. I'm the oldest guy. People usually use this kind of potentials or Lagranges to study the CFT duals and the ADS CFT duals. But the duality is actually string theory and CFT. So what you were doing in principle is more appropriate because you were doing something that comes from string theory. And if you don't find something that matches there, what can you say about that? Is because the other way around, people say, I don't know, maybe.
So we didn't find black holes,
Yes.
except analytical solutions, but we did find them numerically. So
Which systems?
Not for this one. So this is simpler to work with, but so essentially in 4 dimensions, this is dual and modified to what Kakru and company did originally. So they didn't have a scalar potential, and instead of the potential scalar field, and instead of this potential, they just have a cosmological constant. So in fact, their 4-dimensional empirical action is dual to this, not this without this, and this just a cosmological constant and no scalar field.
But what they use, can that be derived from string theory?
No.
So the duality is not clear
No.
that exists there.
No, in fact, that's why, yeah. So the thing is, why did we look for solutions to this, black hole analytical solutions to this, is because this looks much more closer to a stringy supergravity, in the sense that this, if you can always dualize and find the Chen-Simons version, say, of this one, of this action.
And you use Roman supergravity because you like
Romance, yeah, we did romance and all the no, and we need first to find the Lifshitz solution. That we find in 6D and in 5D romance, and that didn't match.
Okay, so I recommend that we proceed to the tea break now. So let's thank you.